Today we are talking about some work we've done regarding forwarding, primarily in the ad hoc case, and kind of looking at a sort of forwarding only approach rather than with routing. I will say in advance, I think a lot of this was started and kind of finalized before I was 100% that Varun was going to be presenting some of his work. So occasionally some sweeping statements I make might not necessarily now be true, but a lot of the impetus of his work was about the tendency of there not really being that many good options in terms of like ad hoc focused approaches to NDN. A lot of the earlier work has been generally wired, and while there is some work with like MANETs, it tends to be more oriented towards VANET cases. These are your things like your CCLS and Navigos and that sort of situation. This is kind of a shame. There's a lot of quirks of sort of ad hoc environments, especially in like MANET networks in general, that don't really get addressed. We have these strongly dynamic networks, things where network partition is a very high possibility, and paths aren't really necessarily predictable beyond at least neighbors, as long as those are within range. And moreover, there is a tendency for a lot of especially specialized use cases to have very strong bandwidth constraints. I think one of our targets was about 2 megabits per second. And a lot of these are like low power devices as well. Traditional approaches to routing are often unviable and ad hoc. There is, of course, an IP sense, things like OLSR and your various other approaches, but those tend to be a lot more specialized in a way that NLSR isn't. And I know a lot of those end up also, I know there's a lot of also desire to take distance vector approaches as well, which we previously had not had an implementation of. This sort of also kind of trickles down to like forwarding strategies as well. Particularly ASF is the one we looked at. Sort of just kind of more specifically, basically traditional link state routing, especially lots of flooding in networks, poor bandwidth behavior, why NDNDV got made, and can kind of be very slow to converge as well, especially in networks which are like very dense and very dynamic. But the sort of focus on routing kind of belies some of NDN's differences. The NFD forwarder is stateful. We don't necessarily we can react to information without needing necessarily a sort of separate application layer on top of it to sort of make determinations based on RTT and so on. So they aren't necessarily tied to having this sort of full application suite. This kind of was how we refined our focus into looking at pure forwarding in sort of MANET networks, basically. We describe it as wireless mobile here. So one sort of ad hoc networks with mobility and also bandwidth constraints. These bandwidth constraints were kind of, I think, probably the biggest hurdle. Baseline ASF, we'll go into a bit more details if people aren't familiar, but it's the main adaptive forwarding strategy that's provided by NFD, has a tendency to generate very high volumes of overhead in the network. These numbers on the right are from pre-cache, or sort of from a free queuing sample, so it's not necessarily representative of the actual outgoing traffic, but you can see how much of this in general, about 95%, is pretty much entirely due to sort of redundant traffic from ASF. And when we're talking about trying to sort of fit all of that through like a 2 megabit per second network, you can see how it's not really able to operate to a reasonable level. A lot of this is due to sort of ASF's probing mechanism. It's essentially the ability to send redundant interests when normal traffic is received to sort of discover paths and find better ways to get alternate paths that might have better SRTT and optimize for it. It's SRTT-based forwarding after all. But this also is quite obviously like a source of overhead. There are some issues in this that I think we've also observed in wired networks, but we're less pressing. Those tend to have much higher bandwidth, has to be generally more forgiving. The big, I think, design flaw in ASF, and I think the one that was probably the most important to overcome, is the fact that probes are essentially just a copy of the same interest with a different nonce. They are basically transparent to any other node beyond the initial forwarder. This is good because it means that essentially nodes don't have to have any sort of knowledge of ASF to forward these. It is just a normal traffic and will be behaving the exact same way. This is bad because that there is no actual mechanism in ASF to prevent probes from triggering other probes. This sort of chaining of probes, in the worst case, can lead to basically exponential amounts of transmissions. We have a figure here kind of demonstrating like the worst case and sort of how basically at each hop we're generating this large amount of interest, especially in sort of very connected networks as well. ASF's retransmission suppression is such that these can accumulate a lot on a single node, and so we can have nodes sending out, saying, multiple copies of data to these probes, and it ends up causing these large gluts of overhead in the network. This was, I think, probably one of the bigger problems and led to some very high total bandwidth consumption. Sort of with this in mind, with our both goal of trying to find a sort of forwarding-only approach to sort of avoid some of the pitfalls of using routing, sort of in like ultimately there's a kind of floor on how much you can do link state without you have to maintain some amount of network state, etc. So there's kind of a floor in how low you can get overhead. And kind of a general focus on trying to sort of minimize that while maintaining data delivery. We did not necessarily think SRTT was as important, given that these networks are unstable. It's not necessarily guaranteed that we can optimize for paths that much. So it was kind of considered to be it ended up still benefiting from avoiding congestion, but was not our main focus. We accomplished this both through changes to ASF and the incorporation of a link manager as a application. In brief, link manager is essentially just a kind of application to handle neighbor discovery and sort of management. So a node will broadcast its own address, and basically other nodes will be able to both create a sort of face to it, as well as be able to detect if that sort of connection is going up or down. It also will then sort of, with these faces, will populate the sort of fib with sort of some pre-selected prefixes. This is kind of an abstraction just to sort of handle the sort of neighbor connectivity stuff. A lot of this might be more or less through specialized mechanisms depending on your implementation, but this sort of helps basically control the sort of underlying connections. We can just worry about the forwarding side. Said forwarding side is more or less based on ASF. This is adaptive SRTT-based forwarding, as we discussed. Its main structure is a combination of a sort of passive measurement mechanism where RTTs of data are stored and can be used to form SRTTs, as well as a sort of way of sorting faces based on whether or not they received data, in which case SRTT is useful. If they've never received any traffic, we wouldn't have SRTT to begin with, and if they've received a timeout or NAC most recently, it's considered to not be working. We use sort of those combinations sort of create these sorting categories, generally priority working with these sort of sorting those by SRTT and then route cost, and then for faces that are unmeasured and then timed out or NAC'd, we sort of sort those by cost and rank those in this order. We have the table to the right, which shows that more clearly. Probing works somewhat similarly. We maintain this sort of similar ranking, but for unmeasured, we will prioritize sending these sort of duplicate interests when traffic is received to unmeasured faces first, and then basically probabilistically choose one if it's either working or not working, basically sort of in a top to bottom order, essentially. So our two main design points were we called selective backup probing and controlled probe propagation. Selective backup probing is basic on the idea that SRTT sort of optimization is not necessarily realistic or optimal in these networks. If paths aren't guaranteed to be consistent for all that long, we don't necessarily think it's best use of our time to sort of optimize for that. However, the probes can still be useful for establishing reachability, however. So in this case, we essentially say that if there is a face that would be usable for forwarding, either the one that was chosen for forwarding or if there's any additional ones, just do not probe. So basically don't get any sort of additional, don't explore beyond the existing faces. if there is at least one that's marked, one that has is currently retrieving data. We tried some other approaches. This essentially kind of leads to sort of reactive probing, but on sort of a periodic timer. Probing has a sort of timer, if I had not mentioned that. We looked at having both multiple next hops, which ended up generating too much traffic. Like a lot of the time, it wasn't necessarily guaranteed that we'd have at least 2 paths at any given destination. And a purely reactive method without the sort of periodic timer would generate a lot of overhead if during cases of failure. Like network partition, for example, if a prefix couldn't be reached, it would just generate probes almost incessantly. You can kind of see how this integrates into the probing workflow. I won't spend too much time on this diagram given our time constraints, but you kind of see that we basically just sort of make a relatively small insertion into this path to sort of accomplish this. Neither of these changes are all that complicated. It's mostly just design considerations for ad hoc. Controlled probe propagation circles back to what we discussed in the introduction. Probes triggering probes leads to large volumes of overhead, and we need a way to resolve that. Our approach, as we chose a fairly simple one, designate a sort of unique fixed knots for probe interest to be assigned to. For these as normal, basically, for interest with this knots, we don't send probes if they would otherwise be sent. We just essentially ignore it. And because this might cause loops from duplicates, just don't send NACs back. Just drop it as we would normally for the loop prevention. This prevention of probes triggering other probes brings our essentially growth of transmissions down to sort of a quadratic growth, which is still not necessarily optimal, but fundamentally speaking, at least each hop can generate one additional probe and so on. And it is significantly better than what we were able to accomplish previously. You can see here how this integrates to the probing workflow at the simple Boolean at the beginning. Our final test was sort of in combination. We ended up calling this ASF Lite for paper we're working on, but because these are interacted in sort of the probing workflow in 2 different spots, it made sense to try and see what the combination was because they don't necessarily counteract each other in any particular way. We did some evaluations in Mini-NDN briefly to go over our model. We had 2 sort of groups of mobility using reference point model. We won't go too much into depth into this. Each group has 1 node designated as a group center. This is purely for application purposes and not for mobility, and 9 for sort of we call group clients. This leads to a traffic model which has 2 different kinds of traffic patterns. Configuration traffic. This is essentially from the client interest to these group centers. This is sort of meant to sort of roughly be requesting a sort of larger file. Each one sends 10 interests every 200 seconds or so to each of these group centers to request 10 data back and sort of equal size. And there's sort of some spacing there. You can kind of see a diagram of how this will flow, though obviously it's 1 interest. We don't want to draw all 10. For the group centers, they instead have what we call the update model. This is pulling from all the client nodes. So each group center every 5 seconds will try and pull 1 interest from each of these client nodes. Basically, this is sort of more of a like periodic sort of update mechanism. So in metrics, quickly looking at like a normalized satisfaction ratio, we had done some, because our mobility behavior was reproducible, we were able to sort of pre-compute some routes to try and get a sort of optimal forwarding value. And we also look at the RTT of data and sort of traffic distribution. The main point in terms of our evaluation was probably the overhead. This is receiver side. This is some quirks with T-Shark. This is considered to be the more accurate number of the 2, but you can see how the disparity between in this sort of 2 megabit per second bitrate network, you can see the disparity between like baseline ASF and these various changes. This combination change, of course, is the most significant. We see around 98% reduction median overhead and a 74% in max. the changes kind of interact with the overhead in different ways. Selective backup probing reduces the rate of probing. The controlled probe propagation does more to control sort of worst case scenarios, sort of brings down the maximum, but doesn't necessarily impact the frequency. So in concert, these help to both lower the frequency of probes as well as lowering the sort of rate at which they're generated. This does not actually have that significant impact on the on the sort of data delivery. ASF itself, because of how much overhead it's generating, seems to be triggering quite significant congestion. We also see observation of this in terms of the RTTs and so on, but it's able to essentially prevent itself from being able to achieve more than about 50% data delivery even after all this normalization. While in contrast, most of our changes, once the sort of overhead is battened down, are able to achieve pretty near optimal results in most of these cases. To the left, you can also see the application traffic numbers. This is not necessarily just good put, as it also as these are sort of measured on each interface in the network and totaled. So it also impacts sort of paths, path lengths, and so on. Controlled propagation has more periodic probing and has more ability to optimize for SRTT than the rest do because of SPP essentially removing that functionality. So it's somewhat intuitive that that's going to generally have better median and RTTs and probably shorter paths overall. And once again, with the congestion, the sort of scaling here kind of makes it hard to really make too many conclusions. Controlled propagation, once again, has slightly better median RTTs, but broadly the lack of this extremely high overhead from ASF lets the network function relatively normally, and there's not that much difference between these cases. If you look at the distribution of 95th percentile RTTs between node pairs, we do see that there is still some benefit to the sort of this combination change over the rest of them. ASF isn't even on the figure because readability, which does suggest that I think this sort of bringing down this overhead is still providing some benefit in terms of avoiding congestion overall. So broadly, we've shown this modification to sort of our adaptive forwarding strategy and how that is able to sort of allow us to sort of create these sort of NDN networks in these sort of very bandwidth constrained tests. As I said, in ASF, it's not able to function effectively, and in LSR has generally not shown similar results in the sort of small scale tests we did for that. This combination change seems to be the most optimal. Probably the reduction in probing might have some impacts on latency, and if that is a concern, probably selecting one of the other changes on their own might be more helpful, but it does seem to produce the best overhead metrics by far, with very little impact in our test case with sort of data delivery. We do kind of hope that this can be used as sort of a jumping off point. As I said, this probably isn't the end-all be-all of MANET forwarding strategies, and there are obviously going to be more comparisons with NDN DV and so on as these solutions become more available. But we do think that sort of a discussion of how forwarding and overhead is being used, how this sort of impacts both wired and wireless networks, as well as how this can be applied to potentially other forwarding strategies in the future might be useful. That's the end of my slides. I might have talked a bit fast. If people want me to go back and clarify anything, I can go ahead and do so. And if people have questions, I am available.
So it seems to me that this improvement is fairly generic and can be applied in, a lot of cases, not just the wireless mobile network case.
Yes, our specific test focus was on these MANET networks, just this kind of, but we do think that probably evaluation of how this impacts in wired networks would definitely be appropriate. It just sort of, that was sort of just our original intentions with the research.
Okay, good. Yeah, I think it seems to be a pretty meaningful improvement in the general case, and then I think it should be applied in the general case, like in all cases. If it proves to be beneficial in other scenarios. I wasn't sure. It's part of the same question, not really a second question, but the main, I couldn't really read the evaluation part you had at the end. There were many different cases. I wasn't sure what all those combinations were. So maybe you said it, I missed something. But so the question basically is, the leftmost was the, existing ASF. And it seems that in most cases, the problems were due to ASF probes consuming all the available bandwidth, so creating congestion, as you said. So I think you should try, did you try in a case where there are no constraints, or the constraints are much higher than the bandwidth that is consumed by overhead, that is occupied by the overhead, so that you don't have that factor, creating problems?
We did a handful. There was not necessarily anything enough that would be statistically significant. If I recall, I think the performance was not that distinct. I think I want to say I did some tests, some small scale ones, up to about, I want to say about bumping the cap up to about 11 megabits per second. And I remember the performance being similar, but I don't have the numbers for that at hand. So, and it is something I think that would be worthwhile to test, yes, in a more broad sense.
Alex, when you do the evaluation, ASF is just a forwarding strategy, so you also have a routing protocol underlying?
No. So part of the idea of this was to just only use our sort of stateful routing. We have Link Manager. I kind of glossed over this briefly. I'll jump back to the slide just because I didn't want to. It wasn't necessarily the main focus. This is basically just a sort of NDN utility that's mostly just to handle the sort of neighbor handling and sort of the basic fib route insertion. Basically, nodes will broadcast their own address. From a beacon daemon will basically broadcast a node's address. The receiver daemon listens for these beacons. Will create a sort of unicast face to that beacon node, and then basically sort of add these sort of fib prefixes so they can communicate. But we don't have any sort of formal routing. I think it's the kind of important distinction is that this is basically just purely sort of ASF sort of forwarding strategy. And basically this sort of utility sort of handles the sort of neighbor connection aspects.
Okay, but this link manager, they need to propagate prefixes?
We load it with some application prefixes. It's kind of an assumption. We probably could have added a sort of, I guess, prefix announcements. We had more time. Basically, it's assumed that these are either preloaded into the nodes or something along those lines. It wasn't necessarily something we wanted to focus on overly much, as this was kind of a more focused on forwarding strategy as a sort of piece of work. Yeah, as I'm assuming the slides will be public. We have a slightly more detailed diagram of how this works in the sort of end. I just don't know if it's. I don't want to necessarily get into that too much, especially since I believe I'm approaching being a bit over time.